briefly review the consolidation soil compression. Our consolidation soil settlements consists of immediate settlements, which is the right after applying load, and then consolidation we are discussing about, which is time dependent, and then water drain out from our soil. At the same time, soil squeezed out. And the secondary settlements is something like a little bit long-term deformations compared to our consolidation settlements. So we focus on consolidation settlements. Right after our completion of our consolidation process, the excess water pressure becomes zero. Hydrostatic pressure still remains constant. And then excess pore pressures due to applied loading, additional loads, gradually dissipate over time. At the end, zero. Our soil has a memory. This soil condition, totally different. And then this soil behave the way this soil experienced. That's why we take soil sample from out there, and then we gonna do the oidometer tests, and then the output something like the linear and linear, right? The compressive curve. We will obtain such curves from the soils because soil memorize their history pressures. So we apply load, probably there should be some deformations. These deformations represented by changes in void ratio. When you assume the Vs equals to 1, we can simply get such phase relationship. So void area reduced, soil solid more densely packed, and they still remain saturated. This slide explains you how consolidation is going on. The important thing is the x-axis is time dependence. But the calculation for NC clay, OC clay, we only focus on this. But today's topic is these things, this timing. How can you calculate 1 year, 2 year, 3 year, rather than final year of 5 years? When you apply your surcharge, which is the Q, your total stress is something like that. This load supported by pore water. So your pore water pressure is here. But this pore water pressure is not hydrostatic pressures, which is the excess pore water pressures. Still, hydrostatic pressure exists. And then you apply this Q. So water have to resist this Q. So your pore pressure increase, which is excess pore pressures. Then these excess pore pressures gradually dissipate because this water squeezes out here. let's assume we have porous layer here and here. Only bottom one, water squeeze out only this way, but it's gonna take longer time. So regardless of the drainage layers, this excess water pressure gradually decrease. It means that this Q supported by water and soil. The soil's effective stress increase. At the end, excess water pressure becomes zero. Then your Q, additional surcharge. Initially, I mentioned to this total stress, but at the end, which is the effective stress, because this total stress became effective stress. This is the consolidation phenomena. We apply certain loads and then water support at the beginning and then gradually drain out, and your full particles densely packed, causing settlement. But sometimes water still remain inside. What has happened? This left-hand side, the valve is closed. Simply open and close, open and close? No. Most of the phenomena happens in this way, but sometimes we consider on drain. This is a drain. Water should be drained out. That's why we call it drained condition. But what situations is in on-drain conditions? For example, consolidation take 1 year, 2 year, takes more than 5 years, something like that. It's quite long term, right? But I wanted to construct Cooper Dam for the pile installation only 1 year, 6 months. Quite short period. In a short period, water can drain out, do you think? No. Of course, a little bit water try to drain out to natural phenomena, but after installation of your pile, we all take out. So in this case, we consider as on drain. Now, what about this? This sigma jet, something different. The drain conditions sigma jet is the surcharge. On drain sigma jet. High frequency, very shock. In this case, water can be drained out or cannot be drained out. Cannot. And then I will show you our Changi Airport marine clays characteristics. Our study area is the Changi Airport, current Changi Airport. This is the soil profile for the Changi Airport. We have upper marine clay and lower marine clay. And each soil layer has the liquid limit and plastic limit. And then liquid limit, plastic limit. Liquid limit minus our plastic limit, plasticity index. And we also have water content, 70 to 80, very high. And then also we will get over consolidation, OCR, sorry, ORC, no, OCR, OCR. And of course, we've conducted odometer tests to get CV. What is the CV? And we will also on-range your strengths. Probably this soil keeps settling down, settling down, settling down. Hi, Pro, how do you know? We have settlement marker here, 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 here. And then your total station, your rebels constantly measure the heights. You run this, right? Then x-axis is time, y-axis is settlements. And then monitor their settlements. And this is the soil settlements along the depths. Settlements profile. What is interesting is your sand film layer from here to here, your soil settlement from here to here, very little. But in the upper marine clay layer from here to here, your soil settled from here to here, here to here, here to here, here to here. The red one is the soil layer itself quite strong. So sandfield and upper marine clay layer settlements looks similar. But let's take a look another soil layer, another borehole, another region of the Changi Airport. The upper marine clay layers settlements is from here to here, very huge. How come this marine clay settle? Why? Excess water pressures developed right after surcharge load and decrease over time. Probably your surcharge will be placed at this time, I guess, right? And then jumped up your excess water pressure. Then decrease. So your marine clay layer densely packed. Hi, Prof, how do you know? How do we quantify your statement densely packed? shear strength looks like undrained shear strength or drain shear strength. The hollow marked is the before treatment. And then solid one, the field mark is the after reinforcement. We apply the vertical drain. We install the vertical stuff into the ground and the water skis out through that vertical way. It means that we accelerate our consolidation. So let's compare certain 50 meters. Wow, this one is around 30 kilopascal, kilonewton per meter square, which is a kilopascal, same unit. But my soil after consolidations jumped up significantly, right? Our consolidation process and even the vertical drain works very well. So in order to figure out our consolidation settlement characteristics, we do oidometer tests to measure one-dimensional compressions and consolidation behavior.
Prof, can you explain the table just now again?
Sorry again?
Can you explain the table just now, like the 2 slides before this one? Yeah, this one.
Okay. Um, Before consolidation, after consolidations, our soil condition is totally different. Before soil layer of the marine clay is quite soft. When you stepped on this, your foot probably stuck in the clay layer because very soft and loosened. And after consolidation, this clay layer skids out and densely packed. But it's just statements. How do we quantify the consolidation effect? So we can, of course, we can measure the settlements and then excess water pressure. But intuitive way is to check soil's shear strength. We are supposed to measure soil strength. What is the shear strength? This is the soil, this is the soil layer, and then we press, and then it probably fail in a shear way, shear, sliding each others. This is a shear behavior. Most of soil failed in the form of shear failure. That's why our soil's shear strength is important. We have two shear strength parameters. C, cohesion and internal friction angle, phi. Cohesion means how they are attached or they adhere each others. And then the internal friction angle means how they interact each others. Right now, this one is the shear strength for cohesion in terms of in kilopascal. This hollow one is a before consolidation, control areas. So all are ranged from 10 to 60 along the depths. But after the consolidation process, even accelerate consolidation by particle drain, their shear strength, C prime, or even C underlying shear strength, much higher than this. For examples, 20-meter depths from the ground surface. Here's the ground surface, and the 20-meter depths. The control area, original ground, is something like 30 to 45, but improved soil layers at the same depth has almost 50 to 60 strength increase.
Okay, thank you.
Yeah, this soil resists more load. This is the original soil, control soil, just before we saw, right? And then we apply 1 ton as a surcharge. And then your volume decrease because your water squeezed out. And then your settlements increase and reaches a certain level, right? Then apply again, increase your surcharge, and settle again, and stable. Apply more, settle again, stable. Apply more, like that. And then we take the final points of the each loading steps. We will get this smooth volume to apply load curve. This volume probably represented by void ratio, something like that. So we will get this. I will show you one more time for odometer tests. Different videos, bite-sized videos from the one of the university in Korea. This is the clay powder. The clay is now fully saturated. At a certain loading stage, for example, 400 kilopascal loading stage, put up, and then now this load is a total 400. Then we monitor 24 hours. Your dial gauge gradually increase the the specimen settlements and stop here. This last point goes to here. 400 kilopascal, 100, 200, 300, 400, and your void ratio. How do you know? From your soil specimen's initial height. Now your soil specimen's settlement. Initial height changes in height. From this value, you can calculate current void ratio. Probably it's around 0.65, something like that. So every each loading stages, you can calculate void ratio, and then you will get this full set of compression curve. Make sure that your pressures, your effective stress is represented in a log scale. So finally, you will get this. From this curve, we will have initial compression curve, and then margin compression curve, and then expansion and recompression curve. And then this inflection points is pre-consolidation pressures. This is the normal effective stress and log scale effective stress. This curve looks quite intuitive to find out your pre-consolidation pressures, and then also Gaussian curve uh, to get your slope CC. These pre-consolidation pressures are normally determined using the odometer test results and the turning points in the slope of the compression curve. This point is the largest vertical effective stress that soils has ever experienced. After this point, soils looks highly nonlinear. Their volume change up to here very small, right? From here to here, only this amount, right? Because this effective stress smaller than the pressure I have ever experienced. But here's my maximum. After this stress, I can't. I can't resist. I can't stand. So your volumes significantly changed. That's why we can mention that the pre-consolidation pressure is the largest particle effective stress. This is the way we find out our pre-consolidation pressures. I will upload this slide to our websites. You just take a look how to find. Graphically, you can find our pre-consolidation pressures. And then the volume changes can be represented by height changes. And then this height change, this is a HO is initial height of the soil specimen. Delta H is the changes in your heights, can be represented by delta E over 1 plus initial void ratios. From these relationships, you are able to calculate current void ratios. Yes, I know initial void ratio. Sorry, initial soil specimen heights. I know initial void ratio. SEWGS. Can you still remember? SEWGS. This odometer test can be done under saturated condition, right? S equals to what? SE equals to WGS. You know water contents, and then GS, specific gravity, then you are able to know E, which is the initial void ratio. So you know initial void ratio. You know initial source sample. You know sample height changes. How do you know? From the odometer tests. Then you can get current void ratio. Then you can plot the compression curve.